A cosmic dial is set to about 10 to the minus 120. That tiny value lets galaxies form instead of flying apart. The immediate takeaway is, cosmic balance is a self-regulating tug-of-war. Gravity pulls in, pressure and expansion push back, structures can grow. We will open that box carefully with concrete numbers. By the end, the hidden levers will feel obvious. Step into a planetarium dark enough that your breath sounds loud. Overhead, the dome feels straight, not bowl-shaped or saddle-shaped. Cosmologists call that straightness spatial flatness, a zero curvature geometry. Critical density means the cosmic density that gives exactly zero curvature. Care here matters, because curvature sets the universe's fate and map. Einstein's equations link energy content to curvature through expansion rates. If density exceeds critical, gravity wins and space curves like a sphere. If density is lower, expansion wins and space curves like a saddle. At the critical value, the tug evens out and geometry stays flat. Rule of thumb: when omega total equals 1, space is flat. Omega total is the actual density divided by the critical density. Inflation likely pushed omega total very close to 1 by stretching space. After inflation, small deviations grow slowly, so near flatness can persist. We can check the dome using the cosmic microwave background. Those baby universe ripples act like rulers etched across the sky. Planck data show curvature within a few parts per thousand of zero. Numbers also agree with galaxy surveys, which map enormous triangles across space. Using those triangles, angles add to 180 degrees within errors. Today, omega matter is about 0.31 by multiple probes. Omega lambda is about 0.69, giving a flat sum. So the picture is, near critical density keeps the stage level. Cut into a star like an onion, layer by layer. Right at the heart, pressure and gravity wrestle without stopping. Hydrostatic equilibrium means inward gravity equals the outward pressure gradient. Without that balance, stars would blow apart or collapse into embers. Gravity squeezes the core, heating the gas and boosting fusion. Extra heat raises pressure, the star puffs slightly and cools down. Cooler gas slows fusion, pressure eases, and gravity tightens again. This thermostat loop keeps sizes steady for billions of years. Tiny tests: squeeze a gas, it heats, it pushes back. That push is why a star can lean against gravity. In the Sun, the core sits near 15 million Kelvin. Fusion their outputs about 4 times 10 to the power of 26 watts. Radiation and gas pressure together counter the immense inward pull. The central pressure likely reaches hundreds of billions of Earth atmospheres. Energy diffuses outward through layers, then streams away as sunlight. The outer layers adjust gently, keeping the surface temperature nearly constant. Solar flares happen, but the global balance stays remarkably calm. The same logic holds for red dwarfs and giants, with differences. Different fuels and densities change the balance, but the loop persists. Example: in real terms, stable stars give planets steady daylight for eons. Net result: hydrostatic balance is the quiet engine of starlight. Without that balance, galaxies would shred or collapse to tight knots. In a bound system, twice the kinetic energy matches the potential energy. That relationship, written as 2k plus u equals 0, guides dynamics. It lets astronomers weigh halos using speeds, not just light. Fast motions mean deep gravity wells and therefore large unseen mass. Dark matter halos stabilize disks and cradle gas for slow star formation. Those motions are not chaotic noise, they are bookkeeping for gravity. The Milky Way's circular speed near the Sun is about 220 kilometers per second. That speed implies a halo mass near 1 to 2 times 10 to the power of 12 suns. Typical halos extend 200 kiloparsecs, far past bright stars. Galaxy clusters push the idea further, with dispersions near 1,000 kilometers per second. Those speeds demand enormous mass, far exceeding the light of member galaxies. Lensing arcs confirm the mass by bending background galaxies into stretched shapes. Rule of thumb: flat rotation curves signal massive, extended halos. With that clue, you can read a galaxy's weight at a glance. Over time, energy exchange between stars and gas settles the system. The disk thickens slightly, bars form then fade while balance remains. Bottom line, Virial logic explains why galaxies look stable instead of frantic. Now watch a starburst galaxy breathe, like a city at night. Blue clusters ignite, winds rise, and a black hole flickers downtown. Feedback means energy from young stars or black holes regulates cold gas. That regulation decides how many stars form and when they stop. Supernova blasts carry about 10 to the power of 44 joules each. They push and heat gas, driving outflows that can escape a shallow halo. Many blasts together carve superbubbles and reset the local gas pressure. Active galactic nuclei go bigger, launching jets and wide, hot outflows. Those outflows stir, heat, and sometimes expel gas from giant galaxies. The result is fewer new stars and steadier long-term evolution. In Meidi 2, winds race at hundreds of kilometers per second. In Meidi 7, a jet spans tens of thousands of light years. The hot gas around clusters can glow in X-rays for gigayears. That glow shows heating balanced against cooling by repeated energy injections. Star formation efficiency then lands near a few % of available baryons. Rule of thumb: if energy input matches cooling losses, growth moderates. So the picture is, explosions act like gentle governors over time. Example: in real terms, fewer stars form after a major outburst. The galaxy stays redder and more quiescent for a long spell. Net result: feedback keeps galaxies from burning all their fuel too quickly. Roll time back when the universe was a hot, bright ocean. Pressure from photons pushed outward, while gravity tugged the plasma inward. Baryon acoustic oscillations are those tug-of-war sound waves. You care because they left a measurable yardstick across today's universe. Waves raced outward until atoms formed and photons flew free. At that moment, the ripples froze, locking in a preferred scale. Spheres expanded around dense seeds, like rings around a thrown stone. Later, galaxies formed slightly more often on those fossil shells. The scale is about 150 megaparsecs across today. Surveys will find a subtle excess of pairs separated by that scale. That bump appears in maps from SDSS and other deep projects. It acts as a standard ruler to calibrate cosmic expansion history. Combined with supernovae, it pins down dark energy's fraction tightly. Pressure and gravity together set the sound speed and period. The recombination snapshot fixes the radius because driving forces shut off. That radius then stretches with the universe as a whole. So the picture is, today's web still carries yesterday's ripples. Example: in real terms, the ruler refines the timeline of acceleration. With it, we cross-check Hubble's rate and geometry with confidence. Net result: early balance wrote notes that later observers can still read. Look at a chain of supernova candles dwindling into deep black. They are fainter than a steadily expanding universe would predict. Dark energy is a smooth component with strongly negative pressure. You care because it decides the future and slows structure growth. As dark energy dominates, expansion speeds up and distances grow faster. Gravity still binds small regions, but large-scale clumps stop strengthening. The equation of state is near -1 by many tests. That value means density stays almost constant, even as space expands. Constant density keeps adding influence, so acceleration eventually overwhelms matter. Supernova surveys at redshift near 0.5 were the first clues. Later, cosmic microwave background and bow data reinforced the case. Together, they give omega lambda near 0.69 today. Growth of structure measurements independently show slowed clustering over time. If the pressure is exactly minus density, acceleration continues forever. If it shifts slightly or evolves, the fate could change. Example: in real terms, galaxy groups will stay bound, while distant galaxies fade away. Rule of thumb: acceleration turns reachable neighbors into unreachable history. Acceleration kicks in when density plus 3 times pressure is negative. That inequality flips the sign in the expansion equation, making space speed up. Net result: a subtle pressure sign flips the universe's long-term story. Zoom into the first second, where particles collided in blinding crowds. Antimatter met matter, flashed, and vanished into floods of light. Baryon asymmetry means a small matter excess survived those annihilations. You care because that tiny excess became stars, planets, and people. To make it, 3 ingredients are needed in early processes. Baryon number must change, symmetries must break, and timing must mismatch equilibrium. Particle experiments confirm some symmetry breaking in quarks and maybe neutrinos. New physics could add more, hiding at scales we still chase. When the universe cooled, annihilations froze out, leaving leftovers behind. For every billion pairs, about 1 extra matter particle remained. The baryon to photon ratio is near 6 times 10 to the -10. Big Bang nucleosynthesis predictions match that value within tight errors. The cosmic microwave background independently confirms the same tiny fraction. Together, they show the excess was global, not a local fluke. Example, in real terms, nearly all early particles died, a rare few stayed. Those survivors assembled every atom you have ever touched. Rule of thumb, a small bias early can dominate everything later. Tiny violations in laws steer outcomes at critical moments. Net result, a 1 in a billion tip made a material universe. Stand on a catwalk above a glowing spiral disk. Gas clouds crash, shear, and settle into lanes that circle the center. Attractor states are conditions systems return to, despite constant nudges. You care because attractors lower the required fine-tuning across scales. During inflation, rapid stretching drove curvature and old relics toward invisibility. Later, galaxies found balancing acts between gravity, turbulence, and cooling. In thin rotating disks, a ratio called Q tracks gravitational fragility. When Q sits near 1, patches hover on the edge of collapse. Stars then form efficiently, but not explosively, because feedback keeps Q near 1. Turbulence and heating rise if collapse gathers pace and Q climbs. Cooling wins if gas thins out and Q drops gently. Those pushes and pulls herd the disk toward a regulated track. Observations show Q often between about 0.7 and 2. That range appears across many radii and across galaxy types. Starbursts eventually quench as winds evacuate fuel over hundreds of millions of years. Halos also relax toward steady profiles within a few dynamical times. Example, in real terms, strong bars form when Q dips, then dissolve when Q rises. Rule of thumb, balanced systems drift back toward a narrow corridor. At their core, attractors are feedback loops with restoring forces. Net result, cosmic balance often emerges as a natural destination. There is that tiny dial again, still holding the stage steady. Gravity, pressure, and expansion trade momentum, and structure keeps winning space. The hidden pattern is now on the table, not a mystery. The same language explained flatness, stars, halos, ripples, and acceleration. If that helped, stick around for more deep space mechanics. Subscribe for the next chapter.